Liberty Middle School, and I'm going to be attending Colorado School of Mines next year. And you might remember me last year for my project, which involved hiding data in images and sound. And I'm going to bring you something about as wacky and amazing as that this year. And I'm also part of Cyber Patriot, which is a computer security club here at Grandview. It's pretty nice. And I also had the opportunity of interning at Northrop Grumman over the summer. And I'm also have the pleasure of going back next year, as well as potentially following years. So that's cool. So what is iPlay? Basically, my project is taking a camera and placing it over just a game of cards, being able to track the actual movement of cards within that game, being able to tell what those cards are to a computer, and then what the computer will do is figure out the optimal strategy of how to play blackjack based on what it sees, as well as previous experience with what I trained to be 10,000 games. So what was my inspiration for this project? And really, a lot of the concepts that underlie my project are really just concepts of the future. If you look at self-driving cars, they have to know where people are while they're walking on the street. And my project has to know the location of cars. Self-driving cars, you can also put them in simulations where you try and force them to drive safe, give them rewards for driving safe, and penalizing them for when they crash or when they accidentally kill someone. In my project, for my project, really this applies with blackjack in the sense that I reward it for actually winning, and then I penalize it for when it does something wrong. And in that sense, it manages to, over time, develop a strategy and figure out the probabilities of blackjack to figure out the most optimal strategy at any given time. And I also got a little bit of influence through an augmented reality card project, which really pushed me towards the direction of doing something with cards, because it just seemed really cool that it manages to track a card and actually put a nice little figurine over it so that you can sort of tell something about it. And it isn't up here, but I was also inspired by Mario, which is an AI that can actually play Mario through trial and error over time. So what are my objectives going into this project? Obviously, I wanted to develop an understanding of those futuristic concepts that I was talking about. That machine learning, that understanding of object tracking and what goes into that, as well as learning the ins and outs of Python, as well as other computational libraries, because I never really looked into Python before, and I heard a lot of amazing things about its potential for programmers in terms of the computational world. I also wanted to strengthen my programming knowledge in Linux. I know a lot about Linux because of Cyber Patriot, and if you don't know what Linux is, it's similar to Windows or Mac, and it's really a nice environment for programmers to develop in as well. And I also wanted to develop a stronger understanding of communicating between computers, because initially I thought that my project would be very resource intensive, so that I would actually have to communicate with another computer in order to be able to do some of the more complex calculations. But over time, I've realized that my project actually works pretty well even on my laptop. It doesn't actually hog that much memory in order to actually do the calculations and all the process. So why don't we talk about my project logo, which will be hanging around in that upper right-hand corner for most of the slides. The main reason why I designed it this way is it's a physical representation of my project. It's a bunch of cards laid out, and there's an eye over it, which is basically just a camera looking over a bunch of cards. And the reason why I picked the colors red and blue is because red just demonstrates that exhilaration that you feel while playing a card game, and that blue reflects that trust and dependability of my program to be able to make the right decision at any given moment. And my company name, it's a nice pun on I play, because I'm playing. And I'm eyeing your play, so I'm looking at card counting pretty much. Oh, nice. People actually like that one. So my advisory list, I'd like to thank my advisor, Dan Parisi. He's a senior software engineer at Trustwave. He really helped me a lot in terms of figuring out the direction of my project and really just supporting me at times where I would run into issues and we would talk just face-to-face about how to look at a situation through a programmer's lens and to figure out how to solve issues that I would run into. And then my advisory list for my support advisors, we have Dan Krukov and Olga Malainen. They're in the audience as well as Dan. And they're both really nice. They're pretty much really moral support. And I also could consult them with certain issues because they are really experienced with the technical side of things as well. And I also have Sam Mock and Tyler Giacomoto as my support advisors. They're both senior project students. And the reason why I picked Sam specifically as one of my support advisors is because he's actually had experience with a lot of the things that I'd be working with. Because one of the things that he was doing was looking at the tracking of movement of people in and out of a building. So I took some of the research that was involved there and I applied it to my project for a little bit of the card tracking aspects of my project. And of course we have the one and only Rob Combs, who is of course the greatest person ever, I guess. Yeah, that's just me. Now why don't we jump into the heaviest part of my project, which is really just the actual object detecting and tracking. How exactly does a computer know that an object is there? And how do we exactly know that it's a car? So what I basically do is I take just a still image, which is pretty much just the initial condition of like a table. So like there's nothing on that table, there's nothing that's been moved around. And then what I do is I take another frame of video whenever during the game, and then maybe there'll be a card on there. And then I compare it with that initial image, and then I perform an image subtraction, which pretty much produces a result similar to this. You can kind of see it. There's like a guy looking through a telescope. And there was also an initial image where there was like a nice mountain range in the background. And this is just showing that there was an actual new person in the scene. So this is how you pretty much tell that there's a new object in the scene. And then what we could do is we could calculate the contours with OpenCV, which is the Open Computer Vision Library. It helps you manipulate and work with images. And pretty much what you could do is figure out the dimensions of the object, which you could then do things with. There's a little bit of code in terms of the process there. I apply a blur just to remove minor pixel differences, because sometimes that would get picked up and that would mess up the detection. And then there would be a simple absolute difference function that would be run. So this is a video just sort of demonstrating that, just so you have a little bit of a visual aspect of how that's happening. The still frame was basically the ceiling, and this is me looking over at my laptop. And there's also like little green lines, which are really just like a line between 2 points between the frames in order to track the actual movement of my face. And then I could expand that out to multiple frames, but I just left it at a frame, just for demonstration purposes of the concept that I was talking about. So after I researched that, I then looked into actual server communication, because I figured the next things that I'm going to go into are going to be really resource intensive. I'm going to have to take those contour results, and I'm going to have to tell my computer which one of these are cards and which one of these aren't. So I looked into the TCP model, which is basically just a way of establishing a secure connection between two computers where data doesn't get dropped. And then we pretty much bind and listen to a port, which you could think of as plugging in a USB to your computer. So it's ready to send and receive data between your computer and the actual USB. So then it connects, and then it actually has to send the length of the data that it wants to send. And this is primarily to ensure that that all of the data there is sent, so that it doesn't preemptively stop reading and then the data is cut off and it's corrupt. And then the server actually listens until it gets that amount of ones and zeros which it got from the line. And then I looked into machine learning after I coded the communication sides of my project. And the best way to visualize machine learning, because it's a very complex concept, is the iris example. I'll go into that on the next slide. But another concept of machine learning is creating classifiers and identifiers for data. So what that means is everything can be quantified by numbers in this world. So what you basically do is you get the numbers which are associated with an object, throw that on a plot, and then once you have enough data built up, you could start seeing trends with the data, which you could then use to make future predictions. So this is the iris data set. This is the visualization of machine learning. Basically what the iris data set is it's just a big data set of iris flowers, and they're all separated by species, and then they take characteristics of them like their petal length and width and other characteristics, plot them on this graph, and then you can start seeing that there's certain fit lines that you can actually create in order to partition the data. So that then, when you get a new point, you can pretty much plot it on and say, okay, that's most likely to be a Setosa, or whatever other flower that you're classifying. How does that apply to my project exactly? How do I take this numeric data of just lengths and widths, and how do I translate it to actual pixel data and actual images? That's a little bit more abstract. And there's a library actually for this, which makes this process much easier, and it's called DLIM, which is basically just machine learning with images. And it also comes with a tool where you can draw boxes in order to define, say, what a card is. And then you can pretty much teach it over multiple repetitions of images what a card is over time. There's also multiple implementations of algorithms that I could use, which would then allow me to pick the most optimal algorithm for detecting a card if I needed to with minimal changing of my code. And I started with a simple object detector. And this is just the tool ImageLab, which pretty much is where I pretty much draw the boundary boxes here. I'm telling my computer this is a card. I got to do that about 500 times during a break, which was kind of depressing, to say the least, spend your break drawing cards. But after all of that, after all of those results, and kind of teaching it what a card is, here is me actually moving a card around and it detected it. Now you might notice that I'm a little bit timid in moving it and I actually don't turn it over. Now, the fact that I didn't turn it over, I actually didn't realize that I had a bug in my code until like 2 months ago, where it actually had a bias for detecting the backside of a card. So I'd actually have to go back and make more template images to actually be able to detect the front faces of cards. But now it does that pretty well. And with more data, it gets more rotation invariant. So it can actually handle multiple rotations of images, which with my data set, that isn't really possible yet because I don't have enough data trained up for it to understand the complex relationship of rotation. And just move on. Okay. So yeah, that's the drawback where it's not really rotation invariant without a lot of data. Initially, I didn't notice that. So I was like panicking and wondering, why isn't this working? I need to code something else. And also there was another issue of a simple object detector not being able to replicate the complex relationships of holding multiple cards that are overlapping like you see in my logo. Because if it's even slightly obscured, the detection kind of fails because it can't quite replicate all of the relationships on the card. And then the tool for ImageLab also, you couldn't really draw perfect rectangles which enclose that card. But I looked at a solution of including a deep neural network, which if you want to know a little bit more about deep neural networks, I'd recommend looking at Garrett's presentation. But for the simple purposes of my presentation, I wouldn't actually end up using this. But it basically models the human brain in the sense, which is also in a similar sense to machine learning in a way. So you could think of the two concepts as related for the purpose of this presentation. It's able to handle more complex relationships, so it fixed that obscuring of cards that I was talking about. Although there were no Python bindings, which is where I was writing all of my code. And when I decided to code this part in C++, it just refused to compile because there were library conflicts and it was an entire mess. So I couldn't really move forward with that part of my project. But I then decided for a solution for my project, which isn't on the slide, but it pretty much where I would take the simple object detector, and in order to make it rotation invariant, I would pretty much just realize that I just need more training data for it to be rotation invariant, and accept the technical limitation of, well, I just have to hold my cards separate so that it can understand that there are two cards. Then we move into template matching, which is how I detect what a card exactly is. So is it a 6 of spades, a king of diamonds, or whatever. And there were numerous directions that I could take with the library that I was using, called OpenCV, which I talked about a little bit earlier. And there's a function called match template, which is pretty simple, where you just pretty much feed it an image of a template, like a spade, just a simple image of a spade, and then it'll be able to actually detect where that spade is on an image. And if it's repeated, it would be able to tell spades within that image as well. Later, I would realize that there were limitations to match template. I would still use match template in the end for my project because I would modify it a little bit to overcome its weaknesses. But then I would also research ScaleInvariant feature transform and speeded up robust features, which sounds like a mouthful right now, but I'll explain that in a second. So what is the match template function? It's pretty much just providing a template image. I've pretty much already talked about this, where I just provide a template image, and then I'll be able to find that template where it's located. Usually this is used in scenarios like where's Waldo. You just take a picture of Waldo, and then the program will be able to find him in that complex image because it will match the pixel value. But the pitfall here is that it can't really be scaled. So if I take the template image from this distance away from my camera, and I'm trying to detect a card way back here, and detecting whether it's a spade or a club or whatever, it's not going to work because it has the template image of a size which is like this rather than farther away where it's smaller. And there's a way that I go around that, and how I do that is pretty much by taking the ratio of the height of the card when I took the picture, to the actual height of the card of the pixels over here. And then what I can do with that ratio is scale down or scale up that template so that that's not really an issue. And then it's also not rotation invariant. So I can't really handle rotation with just one single template. So what I would have to do is I would have to loop through multiple templates and also loop through multiple rotations in order to be able to catch every single case. This is just a video of the simple match template example. As you can see, it's detecting spades right now. And you can kind of see that it only works at a certain distance, and that was the distance where I actually took the template. And then this is a little bit of the code. It pretty much reads in a template image, and then it basically just does a simple match function. And then it gives me contours of where that template is found in the image, so I could actually draw it out, and you could actually see what that image is. So why don't we talk about SIFT, or ScaleInvariant feature transform. This was the thing that I was looking at to overcome the limitation of the restrictions of simple match template functions, where basically I would run a series of computations on an image, and that would give me descriptors, which would basically be represented by circles, and then they would have a direction, and these are sort of universal to every object. So then what I could do is I could map a certain multiple sets of descriptors to an actual image or a video that I would be going. Although there's an issue of speed with this, because a lot of these algorithms are very intensive. Surf is a faster implementation of SIFT because it just uses different algorithms. But I believe I have a video of that. So you can see with these green lines, it's matching those descriptors. Sometimes it glitches out and draws the box wrong. But it can kind of tell the orientation as long as the image isn't too blurry. And then surf is pretty much the same thing as SIFT. So for the purpose of time, I'm just going to skip over it just because it's pretty much the same thing. And then after I've coded all of these aspects of being able to detect what a card is, and then being able to have the framework for being able to detect what the value of that card is, then we go into the fun step, which is the reinforced learning, and actually being able to know how to play blackjack. And what reinforced learning is you just take that concept of machine learning that I was talking about and just apply some psychology to it. Pretty much what reinforced learning is you give a reward to the AI for when it performs well, when it performs the right action within a certain scenario, and then you penalize it for when it does something wrong. So for in the case of my project, I give it a reward for when it wins and then a penalty for when it loses. And then it pretty much learns through trial and error. So I pretty much just have a dealer which draws up to 16, which is a pretty standard scenario for blackjack. And then I pretty much just tell my computer, here's two actions that you can do. You could either draw a card or you could just do nothing at all. Here's everything you know about your environment. You have these cards in your hand. Your dealer has this many amount of cards. People are betting in this way. You figure it out. I'm not going to tell you how you're going to play this game. and pretty much just plays itself, and then eventually it figures out a trend with the state. And another way to visualize what I just said is through something called the Markov decision process, which is just this decision tree where there's a probability of certain actions occurring, and then there's an associated reward with them. So this is something that I got off of a college lecture. For some reason, there's a negative reward for going to class and a slightly positive one for going to other places which you should probably not go to at school. And there's just probabilities of certain actions occurring and then their associated reward. So in the case of my project, this would be, what's the odds of me drawing this card that I need? And then it'll weigh that probability with the reward that it would receive for drawing that card and getting a 21. And then it'll weigh it against, well, what's the chance of me drawing over 21 and me ultimately just losing? And then mathematically, we could look at this with QLearning, which is really that problem of optimizing rewards, which I've been talking about this entire time. And it also includes future rewards. And this is just the Bellman equation. So there's variables, state, action, reward, and then discount. And basically what this equation says is we want to get the maximum reward based on X, which is a state that we can see. So the cards in our hand, the amount of cards the dealer has, whatever. And then a potential action that we can take, A. And then, in order to optimize it for future reward, because maybe sometimes it's more rewarding to just let it go and then maybe draw later and lose. And then just to optimize the amount of reward that we have. And that is where this second half of the equation comes in, where we consider the next possible state and the next possible reward. And then we discount it with this variable called beta because we don't necessarily exactly know what the future is going to be. So we're not going to worry too much about it. And QLearning usually works through a lookup table. So pretty much you just have a whole bunch of states which you build up, a whole bunch of actions, and then a Q value which represents the reward. Now, blackjack is a really complex game to model like that with just a simple lookup table. So I had to recruit the assistance of a neural network for this. And I used the Keras library with the Theano backend. If you were here for Garrett's presentation, he was using TensorFlow. And I'll start explaining a little bit about neural networks in the next slide. And then pretty much neural networks just allow me to model the state, action, and reward with multiple convoluted functions and weights, which allow me to model that relationship much more because the potential outcomes for blackjack are really vast. And that would be very hard to put in a simple table. So in terms of the neural network structure, once again, I use the Theano backend for this, which is just a library which allows you to actually process with neural networks. And then Keras is just what I use to actually build the neural network. So there's really three fundamental parts to my neural network. There's the input layer, there's the state. Pretty much, if you're thinking about the human mind, we see things pretty much. And that's what we see is the input layer. So it's the cards we have. So I feed it the cards that you have, the amount of cards the dealer has, and all of these other factors into the input layers so that it can start making decisions and churn out these calculations. And then the convolutional layers are just a whole bunch of hidden mathematical functions, which we don't really know about and we don't really need to know about. But there's multiple weights which it adjusts, which are just basically constants in the actual functions to be able to model a game of blackjack. And then the output layer is just all of the potential actions that you can take. So in this case, it's actually drawing a card or just holding on. And then the output would output a Q value, which would basically just be, what's the perceived reward of drawing now or just staying and leaving it as it is. And with the results of all of my research with that, this is 10,000 games trained. And this is an example of where my AI is playing 1,000 games. This is a very optimal, this is the highest number that I've gotten, 420 games, 1 out of 1,000. Usually is around 300 to 400. And this is sort of the output of my code while I'm training it. So it kind of has epochs, which are just the games that it's playing through. An epoch is just a whole game cycle. And then this is actually pretty interesting, and this is actually fundamental to something. The reason why it really overdrawed here on its last game of training is because there's also probability of it actually doing a random action. And the reason why people code these scenarios to just do a random action sometimes is because sometimes there's a more optimal strategy that you can do. So sometimes you just choose to draw another card just because you might find out a more optimal way of playing. It might not necessarily make sense, as in the case of really drawing over, but maybe you was just really angry that the dealer got 21. So let's go into my project timeline. In November, I was really looking at that whole contouring and then the absolute difference part of my project, as well as the simple object detection that you saw, as well as the actual communicating with the server, which I would ultimately end up not using because I realized that a lot of the stuff that I'm doing isn't as intensive as I thought it would be. And then moving into December, I was doing research into machine learning, and then I also looked into DLib and its trained object detector method, which is basically just that whole image lab thing, me feeding images into it. And then I actually recorded test cases for machine learning. So winter break, I originally slated as being a time where I actually record my test cases. And I did that. I tested my simple object detector, but then I realized it doesn't quite work as well as I wanted to. So that's where I kind of shifted into the deep neural network aspect of my project. And then, right as everything was kind of falling a little bit apart because I realized some things weren't working as well, my server that was hosting my website kind of failed, so that's me kind of trying to retrieve data from it. So that kind of cut into my time a little bit. And then things just kind of fall apart here, but then they also kind of get rebuilt over time. So I kind of feed test cases. I wanted to feed test cases into my neural network. I had already done that. I was already testing it, so I didn't really need to do that. So then I was looking into coding and debugging that deep neural network for actually detecting what a part is, to be able to model those more complex relationships. After that, after a couple of weeks of just fogging my head as to why the code that I wrote for the deep neural network wouldn't compile, I then realized that with a little bit of conversation with my advisor and a little extra research about what I was doing before, that I just simply didn't have enough training data to make it actually accurate. So I really didn't need to code a deep neural network, which, all right, that's really depressing. And then I started actually researching into template matching and then testing it with a single super value. And then in the month of February, originally I didn't really have much planned for mid-year presentation, but then I just decided let's throw in a little bit more complex template matching with SIFT and SURF, which is that research that I was talking about earlier. And then the coding of the actual template matching, I had already done that, so I was actually looking into coding applications of simple object detection to multiple rotations, because I realized that SIFT and SURF was really slow. And even though the simple object detector had those limitations that I was talking about, where it couldn't handle multiple rotations, I could still code it in a way where it would take multiple rotations of the template and then work with that. And then integration days. Why I say integration days is because I'm working on multiple parts of the project at once, and these are just times for me to integrate the project together. That didn't really happen though, and I actually had to continue coding that template matching because I kind of wasn't getting it done, so I had to give myself a little extra time. And then I started researching the rules of blackjack, so I actually finally got to the play prediction aspect of my project. Now, originally when I was making my timeline, I really didn't know how I was going to approach my project in terms of play prediction and the actual, whether I should draw or not, so I left it relatively vague. But after going through my project, after consulting with my advisor extensively, I figured out that maybe I should look into blackjack data sets and look into machine learning. Maybe I could plot on data onto a graph and then do a similar thing that you were seeing earlier with the iris data set where I could model that game. Now the issue of that is there aren't really that many data sets for blackjack, so I just kind of wasted a week trying to find something that didn't exist, which was really depressing. But then I realized maybe I should do something like reinforced learning, because my advisor was talking about it, and it's this cool new innovation for the future. So then I looked into QLearning, which is just a method of reinforced learning that involves the Bellman equation that we were looking at earlier. And then that integration day is right there. really turned into researching the Markov decision process just so it was easier for me to wrap my head around the concept of reinforced learning. Because it was pretty confusing when I was walking into it, just like you're probably a little bit confused about the concept before I explained it. And then April, originally I intended this to be a nice, happy, dandy month where I have everything done. I'm just testing out code and I'm just preparing for my final presentation. It was going to be so great of a month, and then it didn't happen. Everything was horrible. So really what I had to do was apply that reinforced learning concept that I learned with neural networks. So I had to do a little bit of research into Keras for that in order to figure out how I'm going to build my neural network. And then I actually had to code my AI, as well as the rudimentary blackjack game so that it can actually play itself and learn. Although I finished that all, and then we're here at the final project presentation. And while my bibliography is running, does anyone have any questions? Andy?
I have a couple of questions. In that statistic you showed, we're at 1/420 out of 1,000 games. Were there other opponents too, or just the?
It was just the dealer.
Just the dealer. And how easy would it be to expand it to other card games like poker or something?
It would be very easy. So the idea of reinforced learning and machine learning is to make it really universal. So basically,